And then what does a sphygmomanometer measure?
No bloody idea.
Under Pressure Part 1, The Full Story, is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description as well. Under Pressure Part 1 discusses what pressure or force per unit area is, how to use it, and some of the methods for measuring it. Part 2 continues the discussion with atmospheric pressure, barometric pressure, gauge pressure, absolute pressure, and vacuum pressure. Pressure is one of the most common variables in chemical processes, and understanding how to use it is fundamental to chemical and thermal processing.
What is pressure?
I feel like it is a force that that exerts itself on a unit of measure to create a certain density and energy.
What is pressure?
I don't know, I don't have an official definition for it.
Okay.
I know, abstractly what it is. Okay.
Do you want to give the abstract definition? Or
Yeah, it's when, it's if two things are, pressing together, it's, the thing in the middle.
Gotcha.
Yeah.
Pressure describes the amount of force that the items within a container have pushing on said container.
It's like a force applied to just force. I'll go with that.
Is pressure the difference in a inside a container versus outside? How much force is being on the container?
Why would you want to measure pressure?
To understand if something has potential to react in an abnormal state of pressure, like gas in a pipe.
I don't know. Maybe I don't know. I'm thinking of planes. There's pressure above, pressure below. I assume you need to know what that is to construct that or other things.
Gotcha.
Yeah.
For the same reason you'd want to measure any other force, mathematical purposes, or physics, I'm assuming.
Okay.
You can measure pressure to determine different, you can determine if you want to know the volume of something, or try and determine other factors, or see its influence on people or molecules or objects.
It can help describe the amount of material inside a particular object, assuming it's of a fixed size or of some predictable size, which is quite useful in many circumstances.
Pressure is defined as the normal force per unit area with SI units of the Pascal. 1 Pascal is equal to 1 Newton per meter squared. Another common unit is the torr, or millimeters of mercury. In 2019, the torr and the millimeter of mercury were both redefined. As a result, the torr and the millimeter of mercury are no longer identical, but they differ by less than 1 part in 7 million. So for anything that we're going to use them for, they are interchangeable. Just remember to look up the difference before you interview for a job at NIST. Additional common pressure units are the standard atmosphere or atmosphere, the kilopascal, the bar, and the pounds per square inch. For help in conversion among the common pressure units, remember that 1 standard atmosphere is equal to 1.01325 bar, or 101.325 kilopascals, or 101,325 pascal, as well as 760 torr and 14.6959 psi.
In a swimming pool, how does the pressure change with depth?
There's more pressure the deeper you go.
Like the farther you go down, the more pressure there is.
Gotcha.
Yeah.
It increases the deeper you go.
Pressure goes higher as you go deeper.
The deeper you go, there's more water on top of each point on top of for each surface. So as you move down, objects in it have more water pushing down on top of them. This is water pressure. So as you get deeper in the pool, your pressure increases.
Let's calculate the weight of a column of water at a depth h and a cross-sectional area of A, which is pi d squared over 4 for a cylinder. We'll call the pressure at the surface of the water P naught. The density of the water is rho. The mass of the water is the density times the volume, rho times A times h. The weight or normal force at depth h is mg. The normal area at the bottom of the column is A. The change in pressure is the weight mg divided by the area A. Simplifying, the change in pressure delta P is mg over A, or rho A hg over A, or rho gh. Written in terms of the pressure P equals rho gh plus P naught. Yes. A consequence is that the pressure doesn't depend on the geometry of the column, just the depth of the fluid. Since the change in pressure is linear with the depth, there are a number of pressure units defined in terms of the hydrostatic pressure of that height of the fluid. For example, a millimeter of mercury, an inch of mercury, an inch of water, a foot of water, or a meter of water. 1 atmosphere is about 34 feet of water, or 10 meters of water. Draft pressures in heating, ventilation, and air conditioning systems are often given in inches or millimeters of water.
What is a manometer and how does it work?
I do not know what a manometer works, and I don't even want to guess with a play on words.
I don't know what that is.
No clue.
Haven't the foggiest, no idea.
Is a manometer something that measures pressure? And I don't know how it works, no.
Manometers use hydrostatic pressure for pressure measurements. If we add up the hydrostatic pressures from P1 to P2, we have P1 plus rho A times G times H2 plus H1 equals rho B times G times H1 plus rho C times G times H2 plus P2. Or, solving for delta P equals rho B times H1 plus rho C times H2 minus rho A times H1 plus H2, and the whole thing times G. For the most common case of rho A and rho C being equal because they're the same fluid, such as for measuring a pressure drop in a pipe carrying water or air, then delta P is just rho B minus rho A times G times H1. So delta P is linearly related to H1.
What does a sphygmomanometer measure?
No idea.
No clue.
Sure. Not sure.
No bloody idea.
A sphygmomanometer measures blood pressure. The original ones were a mercury manometer with a pressure cuff and a pump bulb. Blood pressure is traditionally measured in millimeters of mercury. First try. Let's do an example of a typical calculation involving hydrostatic pressure. We'll begin with a diagram that is obviously not to scale, because the 20 centimeter tall piston is just a little bit shorter than the 19.28 foot column of benzene, and the 2.078 meters of argon is shorter than the 7.480 inches of mercury. The problem reads, a cylindrical piston of an unknown solid rises atop a column of benzene inside a cylinder whose top end is open to the atmosphere and whose bottom end opens into a reservoir of mercury. Attached to another part of this mercury reservoir is a cylinder whose top is sealed and whose bottom opens into the mercury reservoir. Above the mercury in the second cylinder is 1 gram mole, see the What is a Mole video, of argon at a pressure of 1.493 bar, absolute. See the part 2 video. Okay. Because the argon gas is so much less dense than any of the fluids, we can ignore the change in hydrostatic pressure in the gas and treat it as being at a constant pressure. The, again, not to scale, dimensions of the cylinders and columns are given in the drawing. The entire system is at 68 degrees Fahrenheit. What is the density of the unknown solid used to make the piston? The data we have are that the density of benzene is 879 kilograms per meter cubed. The density of mercury is 13,546 kilograms per meter cubed, and the local atmospheric pressure above the piston is 1 standard atmosphere. We'll start the solution with the diagram. Because the mercury completely fills the horizontal reservoir, the pressure at the bottom of the 2 columns must be equal. Also, the change in pressure from the top of a column of fluid to the bottom is rho GH. Anyway, since the pressures at the bottoms of the 2 columns of fluid are equal, we can just add them up and set them to be equal. P atmosphere plus delta P piston plus delta P benzene must equal delta P mercury plus P argon. Substituting in, the only unknown is the density of the piston, although we do have a number of unit conversions to make. We'll assume you watched the dimensional equations video and have no trouble with the unit conversions. If you convert all of the heights to meters and use g in meters per second squared, then all terms are in Pascal. Solving for the density of the piston gives you 11,500 kilograms per meter cubed, or 11.50 grams per centimeters cubed. Here, we have a spreadsheet of the solution. G is the standard value. The pressure of the argon is given in bar and Pascal. The atmospheric pressure is in Pascal. With the density of the benzene in kilograms per meter cubed, we have the height of the benzene first in feet, then in inches, then millimeters, and finally in meters. The rho GH formula gives the pressure of the column of benzene as 50,656 Pascal. A similar process for the mercury gives the height in inches, then millimeters, which, incidentally, is millimeters of mercury, or torr. And finally, meters, which by rho GH gives us the pressure of the mercury is 25,239 Pascal. We could also have done this calculation by using the conversion that 760 millimeters of mercury is equal to 1 atmosphere, or 101,325 pascals. We then calculate delta P of the piston, from which we get that the density of the piston is 11,501 kilograms per meter cubed. There's no reason to carry that many significant figures, so 11,500 is quite sufficient. There is a copy of the spreadsheet on the website if you want to look at the actual formulas in the cells. The takeaways of this video are: 1. Pressure is the second most common process variable to measure. 2. Hydrostatic pressure for an incompressible fluid is calculated as the density times g times the fluid height or depth. 3. Manometers measure delta P's with hydrostatic pressure. Thanks for watching. This video was brought to you by the DOFPro team.